Hello everyone, welcome to another video of GPU programming with Mojo. Today we shall see how Python, being the most popular AI language, meets the most advanced AI language, Mojo, and that is made possible by a state-of-the-art framework called Max. Max is a set of tools and technologies developed by a company called Modular, which has state-of-the-art compilation techniques, which makes this marriage highly possible. Max also provides us with APIs for Python, Mojo, C, and some CLI utilities. So Python can connect to Mojo in one of two different ways. It can directly call Mojo and access all the Mojo programs and kernels that we've written, or it can talk to Mojo in a form of a graph. So it can construct a graph which then gets translated into a highly optimized plan, which is then executed by the Mojo compiler. In this way, Python does its own thing of representing the blueprint and then has access to all the Python libraries like NumPy and Pandas and hands off the execution to Mojo, which then collects the plan and then executes. Simply put, Python becomes the front end and Mojo becomes the back end. And the connection between them is made by that graph, which provides both the parties with a sort of a contract for them to execute. Now, one might wonder, is the graph necessary for every possible use case? For a simple addition, for example, it might not be. But since we are talking mostly in the context of AI, and AI is deeply influenced by networks, namely neural networks, so most of the AI programs will have graphs in some shape or form. So Max graph can be highly utilized in those cases. Now there are certain use cases where a graph is also used. For example, if you are to query a database, a graph is actually built and then executed. So a Python can act as a front end, a graph is built, and Mojo can execute its highly performant code on all the GPUs after accepting the graph. So in this way, Max graph becomes our de facto standard in connecting Python with Mojo. And that will be the subject of video today. Now, this sort of programming paradigm is already established with C++ and Python. Now, C++, C, Julia, all of them have bindings to Python because Python is a very dynamic global language which makes it possible to connect to all these backend programming languages. But inherently, you're dealing with two different languages, in this case C++ and Python. And Python being very dynamic and C++ or any other language might be strongly typed. So you will have to handle the memory copies, the memory location, shared memory locations, uh, copy data from one language to the other in the exact way the other one wants to, and maintain two different repos for this to be feasible. That makes possible or gives rise to two different teams, two different code repos, and maintenance becomes a nightmare when this becomes multi-repo. For example, C++, you will have one for CUDA, one for AMD, one for Apple, and all the other hardware. Suddenly there is one Python repo and 15 C++ repos that you have to manage. And obviously this has been going on for the last 10, 15, 20 years. So we have tools and techniques to make this more manageable, but still the inherent complexity is not resolved. And this is especially true if you have tried to debug a PyTorch program and suddenly resulted in a segmentation fault. It's not, the Python won't give you any more information because it might not be your NumPy array or your torch tensor having a problem. It could be something deep inside the CUDA C framework, which you'll have to unpack, and that's really not possible for mere mortals. Now the Max and Mojo way is the the Mojo being a very highly performant code should be an extension to Python. It should feel like you are writing Python, but then just extend yourself enough to get into Mojo land, write the Mojo kernel, and come back seamlessly. The transition between one language to the other should be so seamless that it should feel like it's one language. And it's easier said than done because the compiler behind it, behind these two languages, should understand that you're switching over, make the switch over easy, make the switch over very easy, and also understand the data types and memory locations that are being accessed by these two languages. So the compiler should have like a unified view of these two languages so that you as a programmer can switch between them without thinking too much. So hence the friction is greatly reduced. And we'll see that in the implementation today. They say a picture is worth 1,000 words. So here you go. There are some built-in useful max graph functions that I encourage you to take a look. You can click on the link and find out. But let's now dive into the implementation. We'll start off importing certain libraries. And as you can see, most of it is from the max package, max driver, data type, engine, and graph. Now, the step one in integrating Mojo and Python is to tell the program where to find your Mojo kernels. So you've written a state-of-the-art GPU program that you want to leverage to interact with Python. You have to first let the program know where to find it. So meaning a simple file location on your workspace. So this could be as simple as finding it in the kernels library or kernels folder. So the first program we are going to tackle is vector addition. It has two types of input, vector A, vector B of 10 elements. You add them to produce an output vector of 10 elements. That's our problem statement. We see that this is a Python notebook. So all the code that you see on the screen is Python. So we have, let's say, a randomly created NumPy array. In your case, it could be something where you have collected this data from a different data source, converted from pandas data frame to a NumPy frame. So those things can happen. But for the sake of the demo, I've assumed that I've received it in a NumPy array. So step 2 in your journey would be to convert this NumPy array into a max tensor. It's very analogous to, let's say in PyTorch, you convert a NumPy into a torch tensor. Similarly, you're converting now to a max tensor. And this is the heart of the program. You have to define your graph. So definition of a graph goes like this. You start off with saying with graph, which is your graph class or struct. You define the name of the graph. You define the input types that you're going to provide. So imagine you're trying to provide input to Mojo from Python. So I said the kernel that we wrote or we are about to show is expecting two vectors, vector of vector A, vector B, both are 10 elements. So we are saying expect, and in this case we said it won't be an array, it will be a tensor. So vector A is a tensor of 10 elements, vector B is a tensor of 10 elements. So we are defining our plan saying we are instructing the graph to expect two tensor types of width, vector width, which is 10 elements. Additional parameter being that if you are wanting to execute this on a GPU, which we are, we will also let the program know. Then we include our location, the path to find the Mojo code. So the Mojo code is expecting two tensors. In Python, we are telling this graph, the max graph framework, saying, hey, this is the input type, expect this to be provided. Within the graph unpacks your input. It defines the operation, which is the execution plan. So it says find the Mojo code with the name vector addition, execute this on device, which could be CPU or GPU. The values to the operation would be LHS, RHS, which is your input. And the output after executing the operation should be one tensor type. So in our case, it's the output tensor of 10 elements. So the shape is provided, and the result is kind of sort of stored in output. and the graph says this is the output that it will provide. So you define the input, you define the operation, we define the output. That's it. And the same three statements keep repeating for every operation you perform. Now, this is a simple graph. Your graph could be more convoluted, but these three um, concepts or elements keeps repeating. Now let's look at the vector addition Mojo code. So it could be found within the kernels folder. So if you just go inside the kernels folder, we'll find vector addition Mojo. This program is no different than the one we wrote a few videos earlier. It's the program where we get the thread index and produce the output. In fact, this is the exact same code that I copy pasted from the earlier video, and there is no difference to the kernel. The kernel code and implementation remains exactly the same. The only convention or additional code that you have to remember is this part. You have to let the compiler know there is a kernel of name vector underscore addition because the graph is expecting it. So this name has to match this. And any compile time parameters you intend to provide should be provided here. Now compile time parameters are within square brackets. It is to instruct the compiler certain things that you know beforehand. We know it's 10 elements, so we don't want to let the compiler guess it's 10 and then produce it. That guessing might take an extra millisecond or two, which we want to avoid. Now with this 10 elements, it doesn't matter. If you have billion elements, 1 millisecond also plays an important role in execution time. The other convention you have to remember is this order in which you provide the arguments, which is within this parenthesis. The first one is always the output. The last one is always the context. Context is always provided or passed by default. So this is provided even though you didn't intentionally name it here in the graph. And this will always be the last argument. The first argument will always be output. In between, you can pass any number of input elements. So LHS, RHS, it could be ABC, any number of elements. The order in which you provide here should be the same as the order in which you define in the graph. So if the graph says LHS, RHS, you will have to define it in the same way. Those are the only two conventions you have to follow. Name the kernel with the name that you provide in the graph. Provide any compile time parameters, but more importantly, follow the order in which you're providing the arguments. This set of code is pretty similar to what you have seen before. It's getting the context to the GPU and calling the kernel. And if you just open up the earlier program, you will see that what I'm talking about. This is one of the earlier programs we wrote. The kernel is exactly the same. Our implementation is get the context, create the buffer, or in our case, create the tensor, and then call the kernel. Finally, once you define the graph, you create a session, you lock and load, and execute the graph. The output is provided. So create a graph, define input, locate the kernel, which is nothing but your Mojo code, define an operation, define its inputs and outputs, and you load and execute the graph. This 5-step process is all you need to connect Python, which might be in your existing code base, to a strong, highly performant, hardware-agnostic Mojo kernel. That's it. There's no compilation of C++, there is no bindings required, there is no 2 repos required, 2 teams required. It's just one repo and a knowledge of Mojo, which mind you, is very Pythonic. So it's like Python code and Python-like code existing in the same repository that you're trying to handle. That gives you state-of-the-art performance. Now let's quickly apply the same concepts just to digest this even better by implementing convolution. So we import libraries. We take a convolution of 15 elements with the convolution filter being 4 elements. Likewise, we create NumPy arrays, convert them to max tensors. We show the location of the kernels. Convolution program expects us to provide a convolution input array of 15 elements, and a convolution filter or convolution kernel of 4 elements. Likewise, we define the shape for both of them, but it's still two tensor types as input. Location defined here. Unpack the inputs, define the operation. The operation output is one output tensor of 15 elements. Some of the parameters we already know is the input size 15, convolution size 4, the data type to be float 32. These are known to it, so help the compiler so that it can better optimize the program for you. And the graph output is provided. Lock and load the graph, and the output is provided, and the output is executed, and the result is stored in the result variable. Now, the advantage of having this all in Python is that since we might not be able to calculate the convolution in our mind quickly, we can write a simple Python program to verify the output, just to verify whether the GPU version, which is the Mojo version, did its work and we got the same output. And it seems like we did. You see that 14, 20, 26 is the same output we provided. That's the power of this program, where Python being very beginner friendly and something that we already have integrated into our daily lives. So we could write some test or unit test framework that can verify the results from a GPU from an existing code base, and hence this connection or marriage made possible seamlessly. And just to finish the loop, we just look into our convolution program. This is the exact same program that we have written in a prior video, with the conventions just followed, where we say we register the kernel with convolution 1D that the graph expects. We follow the same convention with respect to arguments, output being 1, input and filter are the 2. Again, the names can differ, but it has to exist between output and context for it to be valid. Then this is get a GPU context and call the kernel. Now this code you see here, which I didn't go through in detail, essentially we pass input tensor, but our kernel wants layout tensor. So it's a small conversion that I do here, where I extract from input tensor to layout tensor. Again, all happening within the Mojo line, and they're all tensors. So it's a slight variation of tensors that the kernel needs. But again, those are all inbuilt within Mojo, and there is no performance hit. So going back. So the key takeaways are Python being one of the most popular programming language, has a huge community, vast ecosystem of libraries, and perhaps even included in some of your enterprise or personal projects. And Mojo being the new person trying to be state-of-the-art AI language. And the Max framework sort of provides us with a connection between these two powerful libraries that makes this marriage highly possible. And now we get the best of both worlds. We get the pure beginner-friendly version of Python, but have the same performance as a C and C++ without its complexities. The Max graph that makes it possible can be defined in 5 simple steps. Name your graph, provide your inputs, show where the kernels are, provide the operation that you want to perform, capture the output. So I hope you're as excited as I am in understanding Max Graph and implementing state-of-the-art AI applications. Thanks for listening. See you in the next video.